Hello students, so today we are going to learn ideal gas equation and we will see how we can derive ideal gas equation from the basic Boyle's law and Charles law. So in the diagram here I have shown a gas at three different conditions. So in the first picture, let us say this is state 1, this is state 2 and this is state 3. So a state of gas is described by three thermodynamic variables as you are already aware of. Those three thermodynamic variables are pressure, volume and temperature. So let us say in the first state the pressure, volume and temperature of the gas is P1, V1 and T1 respectively. So in the second state, when we are going from state 1 to state 2, suppose we keep the temperature constant. So here we are going to keep the temperature T1 constant and we are going to change the pressure of the gas from P1 to P2. Now the temperature will remain constant, so temperature here will also be T1. Now the volume will change accordingly and let us say the volume in the second state becomes V prime or V dash. Again we are going to change the state of the gas from state 2 to state 3 and let us say this time we will keep the pressure of the gas constant. So P2 will remain constant, so in the state 3 also the pressure of the gas will remain P2. Now let us say the volume becomes from V prime or V dash to V2 and the correspondingly temperature changes from T1 to T2. So there are two changes which we are showing here of a same gas of constant mass. Okay, so in the first state and the second state, when we are transferring the gas from first to second state, the temperature remains constant. So which gas law we can apply here? We can apply Boyle's law, right? You are aware of Boyle's law. That is applied when temperature remains constant, and Boyle's law gives the relationship between pressure and volume. Similarly, in the change from second to third state, the pressure remains constant. So here we can apply Charles law, right? Because in Charles law the pressure remains constant and Charles law gives the relationship between volume and temperature. And one more thing I would like to tell you here, that the temperature T1 and T2 I have shown here, they are represented in absolute scale. What is absolute scale? Absolute scale means they have been represented in Kelvin scale. Okay, so let's start. So for transfer, for change from state 1 to state 2, the applying the Boyle's law, the Boyle's law says that pressure and volume product remains constant if temperature remains constant for a constant mass of gas. So I will write P1 V1 equals P2 V dash. So from here you can write V dash is equal to P1 V1 divided by P2. Suppose this is your equation 1. Similarly, for the second to third transformation of the gas, applying the Charles law says that when pressure remains constant, the ratio volume divided by temperature remains constant. So for state 2, the ratio will be V prime upon T1, and for state 3, the ratio will be V2 upon T2. And from here, what you can write? You can write V dash is equal to T1 V2 divided by T2. And let us say this is your equation 2. Now we are going to compare equations 1 and 2. So you will write comparing equations 1 and 2, and as we can see that in equation 1 and 2 both the left hand side is same, V prime or V dash. So if left hand sides are equal, then we will equate the right hand sides together. So now we have P1 V1 divided by P2 is equal to T1 V2 divided by T2. And now what we will do? Now we will take all the suffix 1 terms on the left hand side and suffix 2 terms on the right hand side. So we will write P1 V1 and we are going to take this T1 on the left hand side, so it will come into denominator T1 here, and on the right hand side P2 will go, so it will become P2 V2 divided by T2. So this is one form of ideal gas equation. I think you already know that. So this form of equation is used in solving numerical problems when a gas changes for its state from one to another and all the three variables PV, PV and T change. Okay, one more thing we can notice here from here, that you see that the ratio of pressure, volume and temperature for the state 1 is same as the ratio of pressure, volume, product and temperature in the state 2. So in general this is true for any state, and we can write that PV divided by T, this ratio is constant. But this is a very interesting constant. This constant is not constant for the different masses of same gas, and it is also not constant for the same mass of different gases. Then what type of constant it is? Actually, it is constant for 1 mole of all gases. And what is mole? If you want to know more about that, you can see my another video. I have explained mole concept there. Okay, so this constant is constant for 1 mole of all gases, and then we call it universal gas constant, capital R. So then R is called universal gas constant, and it has a specific value. So R has SI units. In SI units, its value is 8.314 joule per mole per Kelvin. So from here you can write the ideal gas equation in one more form. So you can write PV is equal to R into T. So important thing to note here is that this equation is valid for 1 mole of any gas. Okay. So here there is a catch. So it is any gas. Actually it is for ideal gases only. There is some deviation for real gases that we will see some other time. So for time being, you will consider this equation is true for 1 mole of all gases. Okay, so what if there are more than 1 moles? So for n moles of gas, so if there are n moles, then the constant will be multiplied by number of moles, means the R will become n into R. So then you will write PV is equal to nRT. Okay, so this is ideal gas equation in another form. And suppose if you have number of molecules given in the question. So suppose if there are capital N molecules, means you are not given the number of moles, rather you have been given the number of molecules of the gas. Then you know number of moles can be written as number of molecules of the gas divided by Avogadro number, right? And what is the value of Avogadro number? That is 6.02 into 10 raised to the power 23. So from here, putting the value of n in the above equation, you will get PV is equal to n upon Na into R and into T. And from here, you see that this R upon Na, because both are constant, R is a universal gas constant and Na is the Avogadro number. So ratio of two constants will be another constant, and this constant is known as Boltzmann constant, and we represent that by small letter K. Then this equation become PV is equal to, this will be capital N, number of molecules, and small k into capital T. So this is one more form of the ideal gas equation. So here important thing is the small k, that is Boltzmann constant. Sometimes it is also written with suffix capital B. So PV is equal to NKBT or PV is equal to NKT. This is also another form of ideal gas equation. So let us also discuss what is the value of Boltzmann constant. So I would like to tell you. So value of ideal Boltzmann constant or Boltzmann constant is 1.38 into 10 raised to the power minus 23, and its value is joule per Kelvin. So you see this is capital N upon R upon Na. R is universal gas constant. Its value is 8.314 divided by 6.02 into 10 raised to the power 23. If you will divide that, you will get the same value for Kb. Boltzmann constant 1.38 into 10 raised to the power minus 23 joule per Kelvin. So there is a small difference in the units of capital R and Boltzmann constant. So unit of capital R is joule per mole per Kelvin, and unit of Boltzmann constant is only joule per Kelvin. So I hope you enjoyed this ideal gas equation and its derivation. So if you like my videos, you can consider it subscribing. That motivates me for making more videos. And you can also post your comments and questions in the comment section. I will surely try to reply them. So thank you very much. Take care and bye bye.